question, the data packets that come into the queue, do they contain only the K centers or also the N over K data?
Yeah, so they only contain the small amount of data, which is the K centroids, and just a pointer into the blob, into the central blob. Right, so the reason for that is that it's kind of inefficient to be transferring large amounts of data continuously. So in order to take advantage of data locality, we can just have a pointer and cache what the pointer refers to.
So each slave would then each time again load that data from the blob?
Well, so not quite. So the thing with the data locality is that, I kind of didn't explicitly mention this, but that once instances are able to once we know that instances are going to get the same partition of the input data set every iteration, then they can cache. And beyond the first iteration, they won't need to access that large data set. Does that make sense?
But why do you then have buddy sets of 3 only, and why don't you have one big bag?
Oh, okay. So, well, the thing is here that the buddy sets are, well, first of all, they're for fault tolerance, and if we had a lot of buddies, like the whole, if everything was in one buddy group, then in this sort of maybe naive implementation, each worker would be polling the queues of every other worker, so we'd have n factorial, total polling. But there is another alternative approach which I'll get to right after this. So hopefully that'll address. Yeah, so here's this alternative approach. First of all, let's represent this buddy group type system as a graph. So let's say workers are nodes in the graph, and edges represent the fact of 2 workers, the fact of a worker holding the queue of another worker for failure. So in this case, the buddy system that I just described it's a disconnected graph that's composed of a bunch of small flicks. So there actually is a better alternative here, which I call cascaded failure detection. So here we can just have every instance in the entire pool. We can first impose a total ordering on them, and then have each instance hold a queue of the next instance. So it creates a cyclic chain. In this case, the advantage is that each instance will hold the next, so there's less traffic, and there's actually better resilience, because if any number of instances fail, except for all of them failing, then we'll be able to detect that and recover from it. So I guess that sort of addresses your question of why that approach. But the thing is, that the reason I mentioned this afterwards is that we haven't actually built it. It's only future work. Okay, so now let's go into the performance evaluation for this system. So system based purely on the cloud services. So first I'm generally going to present benchmarks showing that the system has linear speed up across various variables. So first of all, here's linear speed up across when we scale the number of instances out. So here on the x-axis, that's the instance count. We scale it from 1 to 16 instances. On the y-axis, there's on this side, which correlates to the blue line, is the time taken per iteration for various numbers of instances. And here's the same data, but a speed up version of that. So normalized speed up is linear with instance count. So it scales well here. This is, in case you're interested, with only 1 gigabyte of data. So we will benchmark in the future with larger amounts of data, but that's what we have for now. Okay, so next we have speed up with instance size. So when we get more powerful VMs, essentially, how does that affect the speed up? Here it's sublinear. We have instance size, we have speed up, and sublinear. And the reason for that is that I/O bandwidth, it's sort of a quirk of cloud services like Azure EC2, that although larger instance sizes improve the CPU performance, memory, and disk size, they don't really improve the I/O bandwidth performance. The reason for that is that one small instance, for example, if the other instances on the same physical machine aren't like maxing out the disk bandwidth and the network bandwidth, that small instance will actually get the full capacity of the instance. It's not going to be artificially limited. What that means is that essentially the small and the extra large instances have pretty close to the same performance, although extra large is guaranteed to be high, and small just is probably high. We do, by the way, use multiple threads to take advantage of more cores, but even then, I/O is the bottleneck. Next, I'll move on to some related work here. Existing frameworks like Hadoop, K-means, Spark, Dryad, Spark. All these frameworks do support K-means. Basically every framework supports K-means. What's interesting and different about cloud clustering is that it's built purely using the cloud services, whereas those other frameworks are built using sockets, or MPI, for example, is another way of implementing K-means. All these things are sort of they require additional complication to support fault tolerance. So with sockets, we need retrying. For storage, we need replication and so on. Whereas cloud clustering is able to just take advantage of the services provided by the cloud for that. And then another related work here is Azure Blast, which is an application that is in fact built on the cloud services. But it's it's an NCBI Blast implementation on the cloud, and NCBI Blast is an algorithm to sort of find to do subsequence matching on genes. Azure Blast is built directly on the cloud services. But the difference here is that Azure Blast the algorithm isn't iterative. So the fact of K-means being iterative introduces a lot of complications or challenges into how we build our cloud. Namely that we need to support data locality, and therefore that adds some complications to fault tolerance. Okay, so in conclusion, the summary of this is that cloud clustering shows that it's possible to build efficient, resilient applications using only the common cloud services. And to do this, we use some helpful patterns that we've presented. One is that there is a pattern of using multiple queues. So this unlocks data locality. And then the other is using the buddy system for fault tolerance. Okay, so thank you.
That was good. You went without slides. All right, so questions?
So, start with assuming that a number of queues and number of nodes known ahead of time. Is there a great thought when you have more resources become available, flexing?
Yeah. So we actually do support that. So for fundamentally, cloud clustering doesn't have any issue with adding more nodes. It's able to dynamically add nodes, which just report to the master when they're added. The only complication there is that there's two complications. One is that the partitioning of the input data set needs to be repartitioned to incorporate the new node. So currently we do that by repartitioning and flushing the caches. It could be more efficient, but that's how it is. And then the second complication is the buddy groups for fault tolerance, because buddy groups are assigned by the master initially up front based on some algorithm, and then they're static. So we currently again recompute that as soon as the number of instances workers changes.
You show relative speed of your application as compared to itself. Now, what's the performance relative to the API implementations of the others?
Yeah, so we haven't written Hadoop or MPI implementations directly on Azure, but in general, it's likely to be, approximately the same. I would guess with no data, but because of the I/O bottleneck, there's not really a whole lot of intelligence that goes on in order to speed that. But you're right.
Did you simulate the failure on the implementation?
I'm sorry?
Did you simulate the failure on some implementation?
Oh, so it's supporting failure?
Have you simulated
Oh,
failures just
okay.
to see
Yeah,
what
well,
happens?
right. So I didn't present any performance benchmarks there, but yes, we did kill an instance and see what happened, and it worked okay.
All right, thanks.
Thanks.